Wonderful. Yeah. So I guess it's time to welcome Unpack, and we will be continuing with our QBronze course from yesterday. For those of you who are new, I would recommend going through the Canvas and the GitHub repository for QBronze again, so that you're well familiar with some of the stuff. But otherwise, Jibran is an amazing lecturer. He has been teaching the QBronze course with us for 2 past days. He'll be continuing it from there. Over to you, Jibran.
Thank you very much. Thank you, everyone. Welcome back to our second and a half, I guess, session on QBronze. And we'll pick up pretty much right where we left because we've got reasonable amount of stuff to cover. So just kind of a quick note. So that fair coin flipping question from a biased coin, there were correct answers for it, multiple correct answers for it on Discord. So, and there were some kind of misleading answers as well. So if I haven't responded to your specific kind of answer, I do recommend just browsing through the Discord history and seeing all the different answers, and hopefully you'll be able to pick up just by looking at all the different answers, which one is the right answer. I don't want to actually give away myself during the session, all right? Because then it gets recorded for everyone else during future sessions. Okay, so yesterday we finished off describing our formulation for a quantum bit. Excuse me. It was a slightly simplified version of it though, because we said, hey, we will represent these amplitudes as real numbers. Let's fix my screen. Yeah, that's good. Hello, everyone. Yes. We said our amplitudes will be real numbers, but other than that, instead of complex numbers, but other than that, our representation of a quantum bit looks very, very, very similar to what our convex combination for a classical probabilistic bit was and is. Right, so this is our representation with the constraint that, well, alpha square and beta square, or right, let's just write here, alpha square plus beta square has to equal to 1, with the requirement that alpha and beta are real numbers. That was a definition of a quantum bit. We will have much more to say about it today, and it's in many different sessions. Other speakers will tell you more about it as well. But if you'd been kind of new to quantum computing and wanted to figure out, hey, what is this thing called a quantum bit? Hopefully, this is a nice, precise definition for you. Whenever we are talking about a quantum bit, in a simplified sense, we are talking about essentially a two-dimensional vector where each entry is a real number, such that the square of the sum of the square of the two entries equals 1. Right? Where does that come from? That was the second requirement, that how are the amplitudes connected to probabilities? Well, cosine theta is the amplitude here. Cosine square theta we interpret, because of the Born rule, as a probability. Right, and we just take it as a given for now. There was a question about, hey, where is this coming from? And someone recommended go to a good quantum mechanics, kind of intro quantum mechanics lecture class, and you'll find some good notes on it. So we won't delve too much about where it comes from, but we will kind of talk a bit today about how should one understand it. And reminder again, if you've got questions, post them on Discord or in Zoom as well, and I'll try to take them as we get to them. Alrighty, so pretty much like classical operations on classical bits, we would obviously be interested in what are the quantum operations we can apply on quantum bits. And very nicely, we will just take one way to think about it, like we did last time for classical operations. We said, hey, well, a classical operation should map a probability vector to a probability vector. And then we try to characterize, well, what are the set of matrices that satisfy this property, map probability vectors to probability vectors. We can use exactly the same idea for quantum operations. Quantum operation, any matrix we'll call a quantum operation if it's mapping a quantum bit or a quantum state, if there are more than one quantum bits there. If we are mapping quantum bits or a quantum vector to another quantum vector, then the transformation that's doing that mapping, we'll say, is a valid quantum operation. So let's write that down. What do we want when we want to identify a quantum operation? We want all operations that satisfy or rather that map quantum states to quantum states. right? So essentially that identifies for us or gives us a bunch of constraints. What would those constraints look like? Let's say our transformation matrix, and we'll do this in a more generic way rather than just for one quantum bit. So we have got a matrix U, which is our operation, and we've got some nice big vector that represents a quantum state. Let's call that vector V hat. And it's got its bunch of amplitudes indexed by some I. So alpha I is the ith entry in this vector. And let's say U maps it to another vector of the same dimension. Obviously, we would like dimension to be maintained, right? Because it's a closed kind of system that we're looking at. Essentially, what we are saying is U maps vector V to vector W. And the entries in the vector W, let's say our amplitudes, are supposed to be beta sub I. Julia, yeah, you're kind of 2 steps ahead of us. We are trying to identify the space or the set of unitary matrices. Why exactly are these unitary matrices? That's exactly what we're trying to motivate. Amir asked on Zoom whether or not psi is a spin state in quantum. So we are not referring, just like in the classical case, we did not specifically refer to what kind of physical object we are looking at, right? Was it a switch? Was it a coin? Was it an actual classical bit? Similarly, in the quantum case, we in this workshop won't really get a chance to talk about, well, is this like a spin state, or is this like a photon polarization or some other cluster state or whatnot? We'll just refer to the math behind the quantum state, which is just this vector with the constraints that we identified, right? So for sure, it's not completely satisfying, but because you miss out on the physical perspective. But given the limited time we have and the focus that we have from a CS perspective, that's one thing that we kind of don't get to cover in this workshop. But I'm pretty sure you've got other workshops that are definitely going to cover that already. But for sure, it could be a spin state. Alrighty. So what are the constraints that you would have on U based on this equation? Right? U is mapping V to W. We know V is a valid quantum state. So that means sigma of alpha I squared over all the I's was equal to 1 because it was a valid quantum state. But the same constraint has to be satisfied for the betas as well, right? And the index I kind of remains the same. And that's it. So if you've got a matrix U that satisfies this requirement that the alpha sub I, the sum of alpha sub I square and the sum of beta I square are equal to 1, then the corresponding operation is going to be a valid operation. This kind of nicely kind of links back to the brief discussion we had, that what we have here now is the preservation of the L2 norm, or the Euclidean norm is being preserved in this case, right? And so that, in some sense, is a nice summary change that happens as you go from classical computation to quantum computation. Now, the distinction in terms of what people are in chat are calling, hey, are these unitary matrices, is that for the purpose of our current workshop, we are restricting our attention to have the amplitudes and the quantum states to be real numbers. Similarly, for our current discussion, we will restrict the entries of U to be also real numbers. If you allow the entries of U to be complex numbers, then yeah, you're exactly getting the requirement of what you identify as unitary matrices. But given the restriction to real entries for the matrix U, you're essentially getting orthogonal matrices, right? In some sense, this is equivalent to the requirement that U transpose U equals identity, right? In other words, U transpose can then also be thought of as U inverse, which is the same thing as saying U is orthogonal, orthonormal actually, but like if you allowed complex entries, then this would be unitary, right? And a nice way to also think about this is that U is reversible, right? So this is a nice thing that we'll come back to again when we get to quantum algorithms. When we looked at classical transformations, you can go back to some of the transformations that we identified last time and see that actually not all of them were reversible. What do we mean that they were reversible? Well, the transformation has an inverse. In the case of quantum transformations, all valid transformations will have an inverse, hence they're reversible. Not all classical transformations are reversible, and we'll have more to say about that later today. Just kind of a brief mental note that that's something we'll come back to. All right, so that's a nice summary of what is a valid quantum operation. To get more kind of practice on that, let's kind of see an example of a quantum operation explicitly. But before we do that, something that you have probably already seen in quantum literature is this Dirac notation, or we'll use a limited version of it, just the Bra-Ket notation. So this is just some mathematical notation that we use to represent a column vector when we are doing quantum computation. What are the benefits of that? Hopefully, when we do some of the exercises today, it will become evident that, hey, yeah, some of the computations and some of the representations of quantum states really become nice and easy to work with in Ket notation. But by no means is it a necessity that if you want to do quantum computation, you must use Dirac notation. You can use standard linear algebra notation that you are introduced in matrix algebra class. That's perfectly fine as well. Some people, in fact, prefer to do so. But as you'll see, some computations really do benefit by the Ket and Dirac notation. Well, what exactly is that notation? Well, you take kind of this vertical line and this angular bracket, and you kind of sandwich some symbol in between, and that becomes your Ket. The two standard definitions that we start off with, well, if there's a 0 inside this notation, then that's essentially defining the column vector 0, which is referring to this vector. And so in some sense, the standard basis vectors are being defined by Ket 0 and Ket 1. So the Ket 0, whenever I write this, is just another way of writing this vector. And when I write this, all that I'm representing is just this vector. So you see, the basis for two-dimensional vectors can easily be represented then just by these two Kets. Well, if these are column vectors, then if I take the transpose of them, I get row vectors, and those row vectors are represented as bras, where I just kind of flip the notation around. The angular bracket comes over here, the vertical line comes over here. The symbol in between remains as is. There's an issue of taking the complex conjugate if the amplitudes had been complex. But again, for simplicity, since our amplitudes are real, we don't have to worry about that. We are just taking the transpose of the column vector to get our row vectors. Sarah asks, what did we mean that the Euclidean norm is preserved? What it meant is, so this is the norm of the vector v, right? And so what we are saying is, when we apply u, the norm, the new vector that I get has the same norm as the vector v. And in fact, it's a bit more restricted because quantum states will have norm 1, L2 norm 1. And so it's that all the quantum states will have norm 1, right? So both bronze and nickel, and probably even the annealing workshop, at least the part that I'm familiar with from the QWorld side, won't do complex numbers. But as I mentioned yesterday, if you're doing quantum Fourier transform for Shor's algorithm, and so in some of the advanced algorithms, perhaps that you will see in the classic workshop, for sure you will see kind of some quantum algorithms which are using kind of complex numbers. And so the amplitudes will have complex numbers in them. All right. Is it true that when U is applied to a quantum state, a unique state is generated always? Well, so think about it, right? So an identity transformation will map the same state to the same state itself. But now you do, so if you meant that no two different states won't get mapped to the same state, then yeah, that's correct. That's not going to happen with the unitary transformation. U should also be Hermitian. No, not necessarily. So it's something that we'll just come back to in the slide that we're working on. So being Hermitian is a separate requirement. Being unitary is a different requirement. But it just happens that the Pauli basis that we work with for quantum bits is one of those nice cases. And in fact, the only case where we've got a basis of matrices that are both Hermitian and unitary. So I'll kind of write some stuff on the slide now so people kind of are coming along about what am I actually talking about in terms of unitary versus Hermitian. But before I get to that, let's make sure people kind of at least got introduced correctly to the Dirac notation. So if we write something like this, all that we are saying is, hey, we've got a bunch of vectors that form a basis. In this case, it's called the computational or the standard basis. And then it's nothing fancy. It's just us saying, hey, there's a basis of two-dimensional vectors, which are formed by just taking these two vectors as a set, right? You always make norm, but it is always considered Euclidean norm. All right. Now, this basis is not unique, right? I could take some other basis as well. And in fact, let's exactly see how I could generate another basis by applying a transformation to these basis vectors. And we'll take one kind of frequently, in fact, kind of the poster child example of a quantum operation referred to by the symbol H, which is called the Hadamard transformation. And people who might recall the flip F transformation, the classical transformation from last time, might see some similarities here and also note some differences. We'll talk about the differences soon. But you can quickly verify that this matrix H is indeed unitary and orthogonal, right? Well, if you take the transpose of this matrix, you'll get the same matrix back. And if you multiply it out together, so let's see if people can quickly verify that H transpose H equals identity, right? So this is just the symbol that I'll be using for identity. And in doing so, perhaps you'll also verify that H transpose actually equals H. So as someone previously asked, this is a specific example where the matrix is both unitary and Hermitian, but it's not a general requirement that every unitary matrix has to be unitary and Hermitian, or every unitary matrix is Hermitian. All right. Everyone okay with this claim? Have you verified it yourself? Or do you buy the argument that H transpose H equals identity? So let me make a quick note. So that this was the requirement to be, in our case, unitary. Note that although I'm saying unitary over here, the unitary requirement really requires a complex conjugate rather than just taking the transpose. That's because we are taking real entries. It's sufficient to say that's just taking the transpose. And in this case, again, this is the requirement of what it means for the matrices to be Hermitian. All right. So it's just a classification. Remember, like in the classical transformation case, we said, hey, the class of classical transformations gets a label. We call it stochastic. It's just a label we are giving them. So in our case, the requirement that matrices are unitary. Well, another way of thinking is a matrix is unitary if it's a valid quantum transformation. Well, what does it mean to be unitary? For our purpose, it means you take the matrix and its transpose, multiply it with itself, and you get the identity matrix. Right? So you take the Hadamard matrix, you take the transpose of Hadamard itself as well. Hopefully, we can verify just by inspection. That's going to be the same thing. So we've already got a verification, that this equation is satisfied. That means we've got a separate verification that this matrix is indeed Hermitian because it satisfies this requirement. But now, once you computed that, then you just say, hey, all right, I'll multiply H with itself. And then so what I'm requesting everyone to do and verify is that indeed H multiplied with itself is equal to identity. So that's kind of like a crucial identity that I want to make sure everyone is convinced of. Can quaternions be taken in place of complex numbers? People definitely have worked on trying to generalize quantum theory based on, hey, what if these amplitudes were quaternions rather than complex numbers? And not too much new stuff comes out of it, right? So I haven't really explored that myself, but kind of the general response and summary of what to take away from that is that, hey, it's essentially the same thing that you get. What's the name of the gate? Yeah, the name of the gate is Hadamard. And so that's why we kind of shorthand it with an H as well. And that's something, for a quantum algorithms person, it's kind of a bread and butter kind of transformation. Just like C0 that we saw last time, Hadamard is something that you'll see as one of the building blocks pretty much of quantum protocols. Right. For sure, there's lots more to be said about taking Hermitians and what is the role of Hermitian in quantum mechanics, but we won't really need that for our current conversation. Right. Right, so first, going back to the previous slide, note that all that we are requiring for quantum operations is for them to be unitary. They are not required to be Hermitian at all. So evolution of quantum states happens through unitary transformations. Unitary transformations need not be Hermitian. Hermitian matrices have a separate role. It just happens that in the example that we are looking at, the Hadamard matrix is indeed both Hermitian and unitary. All right. So I'll take it everyone has verified H transpose equals H, and then H transpose H equals Hadamard. Based on that, could people then verify what would be the result of applying H to the state 0? Right, so if you want to kind of expand it out, you could literally kind of just put in the Hadamard matrix in there, put in the state vector, and do your matrix vector multiplication to figure it out. People who already know. Right, so in the general case, when the entries are complex, Amir, yes, it should be dagger rather than just transpose, but we are taking all the entries to be real, so taking the transpose is enough. Ket 0, Ket 1, square root 2, excellent, right? So this is exactly going to be the vector 1 over square root 2 with 1, 1 over here. Writing it in the Ket notation gives me this representation. Right, so as people mentioned in the chat, this is also sometimes referred to as the plus state. Right, so you now see how the Dirac notation is used. The symbol inside really becomes kind of the identifier or the unique label of the specific vector that I'm referring to, right? So in this case, 0 was being used to refer to this vector. Now this plus symbol inside the Ket notation is being used to refer to this, or indeed this vector over here, right? So that's something we should become comfortable with, and that has benefit. What about H applied to the 1 vector, which will be just H applied to 0, 1? What do we get? Right, not the same thing, right? It's slightly different. We get introduction of a minus sign, and that's something nice to observe, that, hey, this now is something different than what would happen in a classical corresponding transformation, right? So if this was the F matrix over here, we would expect something different in terms of behavior, and that's something that we'll just kind of see quickly. But to kind of finish this conversation off, this then is referred to as also 1 over square root 2, 0, minus 1. So the key thing to observe was that, hey, here we've got a minus sign rather than a plus sign. And then we say, hey, this has a unique symbol for it as well, that we write it as plus with a minus symbol. So these two vectors are important enough such that they have their own kind of name for it as well. You've got the plus vector, you've got the minus vector, or the plus state or the minus state. They are referred to sometimes as the Hadamard basis. Obviously, because we applied Hadamard to the basis state, that's why kind of referring to it as the Hadamard basis. What are the benefits or interesting things about the Hadamard basis? Let's kind of see and check, because then we'll also start now seeing how do quantum states behave differently than classical states. Yeah, sometimes you would call it the X basis as well, for sure. Okay, so we'll do a bunch of kind of thought experiments, and we'll try to figure out how do classical versus quantum states behave under similar looking operations, right? So on the left-hand side, I've got kind of a quantum circuit, multiple iterations with slight modifications, and on the right-hand side, I've got kind of the corresponding classical version of it. The blocks are representing the transformation that I will be applying on the state. In the classical state, I'm applying this F matrix that we saw yesterday, which was this notion of a fair coin flip, where the idea was, recall that if I apply F to any probability vector, output will always be just a uniformly random bit. Whereas if I apply Hadamard to either the 0 or the 1 state, I've seen that, well, there's this minus sign that comes out in the amplitudes, but that minus sign doesn't really change what we see apparently in terms of the behavior, right? So if I, based on what we know so far, if I were to measure, if I were to look at the plus state versus if I were to look at the minus state and see, well, hey, what's the probability of seeing this state and the output is either just going to be a 0 or a 1, then, well, I just have to square the amplitude in front, right? And the minus sign in that case doesn't seem to matter, because minus 1 over square root 2 squared versus plus 1 over square root 2 squared both give us 1 over 2. So the probability to see a 0 or a 1 state is indeed half if I apply Hadamard to the 0 state or Hadamard to the 1 state. Right. So let's try to kind of explore that a bit more. So quickly, we'll summarize the classical situation first. So let's say I've got my coin. So we'll think physically, there's an actual physical coin. And I am going to flip it via applying this F matrix to it. What's the output over here going to be? Well, the computation that we did over here automatically tells us that the output over here is going to be the matrix half 1 1. Right? Now, what about this second experiment that we have over here? What if I'm not going to do a single flip, but rather I apply F twice in sequence? What would be the result out? The output state over here, or the probability vector I get at the end. There are multiple ways you can get to the right answer. You can do the explicit computation. You can just make an observation from this, given that we already know the answer, that what's the state after applying F once. So if I apply F twice, what would be the answer over here? We get the same probabilities, i.e. we get exactly the same vector out. So I get half 1 1 out over here. Seems almost trivial so far, right? So this is, remember, the left side is all classical. So the right side is all classical. And this is the quantum case over here. So the right-hand side, sure, you can represent it as kets, but let's kind of restrict the kets for the actual genuine quantum case. Now, what about a slight modification, if you can call it a modification, where in this case, I just said, hey, do the flips twice. And so think about it as an actual flipping protocol that you're doing. I have a coin, I flip it, and then I flip it again. I didn't do anything in between, versus the second iteration of this experiment, where in between, after I flipped the coin, I chose to actually observe, and let that be my eye observing the result of the coin flip. So I did the coin flip, looked at the result, it is a head or a tails, and then I flip it again. Is there something different that will happen over here? No. Good. No. Let's kind of briefly explore it, because regardless of what happens over here, even if I say, hey, in this case, I didn't observe the result, so the probability vector, whatever it was, I know it was this thing, didn't get modified in any way. And well, if I put it into F, out comes the same vector. In the second situation, well, or the third example, when I do the observation, some sense, then the probability kind of goes away, right? I know that when I would have flipped it, the coin would have come up with probability half heads and with probability half tails. But then when I chose to observe the coin flip's result, that uncertainty completely vanishes, right? With certainty, I would know, hey, the coin is in state head or the coin is in state tails. Everyone okay with that, right? It's not really subtle, but it will seem interesting when we will compare it to the quantum case, right? Now, but that doesn't really matter, because, you know, no matter what P is, F will still map to half 1 1. And so, oops, this still gives us as output half 1 1 over here. Alrighty. So now, what happens in the quantum case? The first example is something we already did. If you've got the 0 state, apply Hadamard to it, I will get as output the plus state. If I've got the initial state as 1, I apply Hadamard and get as output the minus state. So you note here that there are these two different states, and indeed they are not the same states. You can verify that the dot product of these two states is 0, so they're orthogonal states. So that's nice and interesting, because in this case, we were actually getting the same state out, regardless of what you provide as input. However, in this case, if I put in 0 versus if I put in 1, I get the plus state out versus I get the minus state out. However, statistically, if I were to look at the plus state or look at the minus state, as we saw in the previous slide, well, it will be probability half that I'll see 0 and probability half that I'll see 1. In some sense, I don't really get to distinguish between the 0 and 1s. I get the same statistics out, right? Everyone okay with that? Right? Good. So now let's see the corresponding quantum version where we apply Hadamard twice in sequence. I apply Hadamard once, then I apply Hadamard again. What comes out? You go back to the beginning, the initial state. Very good, excellent. Because we already verified, right? H transpose equals H, and H transpose is in fact H inverse. So a sequence of two Hadamards applied consecutively will essentially cancel each other out. So the 0 state, if indeed the initial state was 0, then the output over here would be 0. And if the initial state was 1, then the final state would also be 1. Kind of completely complementary to what we noticed in the classical situation of applying F in sequence. Interesting, right? But not necessarily that weird, because in the classical case, the matrix was just a different matrix. So if you do the math works out like that. And similarly, in the quantum case, I'm not applying F. I'm applying a different matrix. And so that different matrix has different properties. It's got this -1. That -1 causes cancellations to occur, hence that interference pattern that we refer to. And that causes this to work out as either a 0 or a 1. Right? Basically, the stuff in the middle just becomes like an identity. For completeness, let's look at the final version where, hey, I chose to observe the result of what's in between. Which I've referred to this, which you can think of as a measurement. For sure, I could, again, make the I as well. What happens now in the end? So I apply Hadamard once, then I look at my quantum state, and then I apply Hadamard again to my quantum state. What do I expect to occur over here? Right, very good, excellent. So people already kind of are following along, and probably from Quantum Odyssey as well. Excuse me. So the measurement in the middle, yeah, causes a collapse, but let's not worry about the collapse, because perhaps there was a collapse in here as well, right? The interesting though is the two Hadamards don't cancel each other out as well. And also, it's not the same thing as, hey, I always get kind of half 1 out in some sense, but I do get kind of go back to kind of the first situation, i.e., if the measurement result over here was a 0, not here, but over here. If the measurement result over here was a 0, then indeed over here I get a plus. And if the measurement result over here was a 1, then indeed over here I will get a minus. And so the deterministic situation over here is completely kind of vanished. And because of this interaction in between, this measurement in between, I do get kind of my probabilistic behavior again. So the measurement in between for the classical case is essentially almost, something that in the classical situation we don't give a second thought to, right? The act of measurement, but when we think about this in this case, it is indeed slightly non-trivial, right? Before we did the measurement of the classical coin after its flip, our level of information about the coin flip required probabilistic kind of formulation, that we knew that with probability half it would have come up heads, and with probability half it came up tails. When we observed the result, we know now with certainty that either it came up heads or it came up tails based on the observation. So that means now it's back to either just the vector 1, 0 or the vector 0, 1. And then when I apply F again on it, well, I get back exactly the standard fair coin flip result. Now, the situation is different in the quantum case in the sense that I have a measurement in between versus I don't have a measurement in between, yield to two different situations in this case, which was not really the case in the classical situation over here, right? And so we won't delve on it too much for now, but it's kind of the starting point for thinking or understanding about how quantum states behave differently than how classical states behave based on whether or not there was a measurement involved in between, right? And that measurement is what essentially you can identify here is that the identity that we were able to apply over here, that two Hadamards and a sequence identity, is not what we are able to apply over here. This measurement in between introduces a discontinuity, for the lack of a better term at the moment. In the standard interpretation, you are collapsing your state. But then again, based on how we concluded our discussion yesterday, isn't there a collapse happening over here as well, that this P1 minus P becomes exactly a 0 or a 1, a head or a tails? But in this case, yeah, again, the plus or the minus state becomes exactly 0 or 1 based on a measurement. I apply Hadamard again on it, it becomes obviously as output a plus or a minus, which is in contrast to if these Hadamards were applied in sequence without any interaction in between over here, right? And all this is due to the fact that, well, if you look at the Hadamard matrix, it's got a different structure. The key thing that's making all this happen is the minus sign, right? The square root 2 versus 2 is more of a normalization issue. The really key thing over here is this minus sign over here, and then correspondingly the minus sign that shows up in the minus state as well. So you note how when we individually thought of looking at the plus state and the minus state, yeah, the minus sign didn't matter there because 1 over square root 2 squared versus minus 1 over square root 2 squared both give us a half. But when we looked at the combination of applying Hadamards and whether or not the input state is a plus or a minus state, and whether or not we're doing measurements in between, then kind of the situation does become more interesting and non-trivial, right? So in our current formulations, we won't go too much in depth about loss of information and how exactly a measurement is corresponding to collapse of measurements. I will, if people are interested, share kind of some papers and references to read up on, because it's more of kind of a nice black hole that one goes into, and you can have as long a discussion as you like without necessarily getting too much meaningful stuff out of it. But it's definitely something that everyone has an opinion on. So we can have a discussion on Discord about that. How we can build a Hadamard gate physically, it can be something as simple if indeed my case was that my quantum state is being viewed as a photon, then just implementing a beam splitter at 45 degrees would essentially apply a Hadamard to this photon. Right, so a simple, perfect mirror inclined at an angle of 45 degrees to an incident photon will essentially correspond to applying a Hadamard on that photon state. Right? Right, so Vivek, so I'll leave it up to kind of your understanding, discussion about, hey, is there a collapse happening in the classical case or not? Does it even make sense to talk about a collapse and whatnot? But I won't speak about it too much right now, maybe in a few slides. Really pressed for time today. Does QDITs include QTRITs too? Yeah, QDITs. Tahir asks about QDITs. So QDITs is the general term for any higher dimensional quantum state. Right now we have qubits, BITS. So that's for 2-dimensional. QTRITs will be 3-dimensional, and QDITs will be D-dimensional. Right? Okay. Good. So based on kind of what people are kind of asking about in terms of measurements and collapse and whatnot, there's this nice kind of picture from some popular survey that happened at the end of a conference nearly now 2 decades ago, where, so this is a conference with experts in quantum physics asking other experts in quantum physics about what they believe is their favorite. So yeah, the top part is kind of, what is your favorite interpretation of quantum mechanics? And they had all these different options identified over here. You note that the bars over here don't sum up to actually 100. It's more than 100. And so that kind of shows how people were actually perhaps not taking the survey seriously, or the fact that, yeah, you can have more than one favorite interpretation of quantum. And indeed, kind of, despite all the work, the standard wave collapse kind of interpretation, Copenhagen interpretation, comes out as perhaps the most popular. But more interestingly, though, Asher Perez, one of the pioneering quantum information scientists, got up at the end of this conference when these results had been announced as well from the survey and said, and who among here believes that the laws of nature are dictated by a popular survey? So take what you might want out of it. Alrighty. So we've got classical and quantum kind of coin flipping done. Perhaps just in terms of completeness, we want to know, how do we combine quantum states together? Well, that, as I mentioned last time, is going to be very similar to how we do it for classical vectors. So a quantum state is alpha 0 plus beta 1. Phi, let's say, is gamma 0 plus delta 1. And if you combine them together, well, I will write it as psi tensor phi, and that will be alpha 0 plus beta 1. And so the computation itself is exactly the same tensor product computation that we did with classical vectors. What I'm just doing is writing down that computation in terms of the Dirac or Ket notation, so that you see how that computation, that same computation, is done using Ket notation. Gamma 0 plus delta 1. And so that will give, and you can think it works kind of almost like how you would multiply out algebraic polynomials, except that you remember that, hey, this is a vector that lives in a different vector space. So you've got to remember that. And so you will get like alpha from here, gamma from here. And now the interesting thing about Ket notation, you say, hey, well, this is the first 0. So maybe I'll uniquely identify them. So this 0 is this 0 over here. And then you say, hey, this will be tensored with this other 0. Let's write it in black. But this other 0 is the one that came from here. And so that this is probably one of the key things that confuses people when they initially get started working in Dirac notation computations. Hey, which is which 0? And so just make sure that you remember the order, and then everything should work out fine. And for sure, as Jorge is writing out, you could shorthand it as 0, 0, which I'll just do in kind of the next line. But let's kind of finish this off first. This will then be also alpha delta 0 tensor 1, and also beta gamma 1 tensor 0, and finally beta delta 1 tensor 1. And so what we'll do is, now as we become comfortable with the notation, the 0 tensor 0 could be written now as just 0, 0. I dropped the tensor product in between, and then I realized, hey, I don't even need this bracket notation in between. I could just write it as 0, 0. And so this whole thing then just becomes alpha gamma 0, 0 plus alpha delta 0, 1 plus beta gamma 1, 0 and beta delta 1, 1. And now perhaps you see one of the benefits of writing this out in Dirac notation is that the label over here in the Dirac notation itself is nicely identifying for you the index of the vector in which you'll see the corresponding amplitude, right? So if I were to write out this vector in standard vector notation, this would be alpha gamma, alpha delta, beta gamma, and beta delta. And we observe that, hey, this is index 0, 0, this is index 0, 1, this is 1, 0, this is 1, 1. And you note, hey, this is exactly the index that appears, the label that appears in the Ket over here as well. So this is really, really kind of one of the nice things about the Ket notation, that once you have got this right way of labeling things out and do the tensor product correctly, especially for sparse quantum states, you've got a very nice, concise representation for writing those states down. All right. Any questions about this representation? I think, right, so Rasesh asked whether this is entanglement. So that will depend on the choices of alpha, beta, gamma, delta, right? So it's one of the topics that exactly we'll be moving on to next. If I choose, for example, alpha delta equal to 1 over square root 2 and beta delta equal to alpha gamma, so this equal to 1 over square root 2 and this equal to 1 over square root 2, then yes, indeed, it's one of the maximally entangled Bell states. But if you choose all of them equal to half, then it's not a Bell state. I did not understand the vector of the Greek letters. The vector of the Greek letters, well, I'm just saying that, hey, this vector, in fact, is exactly the same thing that I would have obtained if, let's say, I had vectors alpha, beta, tensor product with gamma, delta. And if you recall, now, if you think of this as just PQRS, the way I label the classical probability vectors, then it's exactly the same computation that we did with the classical probability vectors, right? So I'm just changing the English alphabets to Greek letters and then applying exactly the same computation. So that's kind of, again, a nice observation. Combining the systems together, we are applying exactly the same mathematical operation that we did for classical probability vectors as well. There's nothing new there. The combination process is exactly the same tensor product, whether for classical states or for quantum states. It's the fact that the basic primitive, the quantum state in of itself, is a different beast than the quantum state. QQuart, is that the name for a 4-dimensional quantum state? QQuart, yeah, if you wanted to think of it as a single 4-dimensional quantum system, perhaps QQuart. I'm not sure whether that's the norm though. Anything after tritz is just labeled QDits for D equal whatever value you're working with. Alrighty. There's a nice another thought intuition that you can develop over here in terms of when quantum systems will be of interest. So someone already referred to, hey, is this entangled? And let's say a little bit more about that over here, even though we want to do other stuff as well. Imagine if this was now not just 2 qubits, but n qubits, right? And you would do exactly the same tensor product, exactly in the same way as you would do it for a classical system. So let me try to formulate the question precisely, and then you can answer on Discord. Imagine I had a quantum system of n qubits. I wrote it out together by taking the joint tensor product. Could you identify a specific case when that quantum state can be simulated efficiently on a classical computer? I'm not necessarily asking you to identify exactly all cases, but one case. So you took a large n-dimensional n qubit system, and you took the joint state of that quantum system. So you took the tensor product of qubit 1 with qubit 2 with qubit 3 and wrote it all out. Is there one special case which we can simulate efficiently on the quantum in the classical case? Right, so I have a system of the form psi1, tensor psi2, tensor psi3, each of them qubits up till psi n. And I'm taking the tensor product out. Ijaz mentions, I assume it's Ijaz product states. And in fact, the way I'm writing it down automatically implies that it's a product state, which is kind of the complement of entangled states, as long as we're talking about, states, pure states. Don't worry about it. So what's happening here? We are saying that I have, going back to what we mentioned yesterday, right, that there can exist 4-dimensional probabilistic systems, vectors that cannot be written as a tensor product of two-dimensional vectors. And we said the same thing will hold for the quantum case as well. But now in this case, the way I'm representing the state itself, that there are n quantum systems, there are n quantum bits, but each of them is its own independent system, because I can write them out as quantum bit 1, tensor product quantum bit 2, tensor product quantum bit 3, such that I get n quantum bits. Now, if I wanted to do the evolution of this quantum state, as long as I've got a guarantee that the n quantum bits will always remain, or will always admit this decomposition, then you could always just remember the amplitude, the single amplitude, let's say alpha 1 of psi 1, the alpha 2 of psi 2. So, let's say they have this representation, alpha 1, beta 1 for psi 1, alpha 2, beta 2 for psi 2, up till alpha n beta n for psi n. And if the quantum state always has this decomposition, even as you are evolving it over time, then I just need to remember, let's say, the alpha sub i's. And that's enough information to remember the entire quantum state. Try to convince yourself of that argument in terms of why. If I evolve the quantum state and I have got this guarantee that the state at any given time can be written as a tensor product of the n individual quantum bits that make it up, then a classical computer can indeed efficiently simulate it, because it just needs to keep track of the individual amplitudes of each quantum state and then just multiply it out together. So that exponential increase in the dimension of the state doesn't really help over here in terms of a quantum advantage, because the classical computation can efficiently simulate it. So that means automatically that if a quantum state is going to offer a quantum advantage, it does need to be entangled. And so entanglement will for us mean basically whenever the quantum system cannot be written down as a tensor product of its individual components. And I'll talk a bit about it in just 2 more slides. Right? So that's something to keep in mind in terms of one case where classical and quantum are equivalent, or classical mechanics or classical computation can efficiently simulate quantum computation. I'll repeat it. So classical computers can efficiently simulate quantum systems or quantum states if you've got a guarantee that the n individual quantum bits have a representation that admits this tensor product decomposition. That is, you can always write it as psi1, tensor psi2, tensor psi3 up to psi n. All that the classical computer would need to do is to remember the individual amplitude for each quantum state, and then just multiply it out at whatever kind of time of the evolution you're interested in. And so the classical computer can reproduce the probabilities the quantum computer would produce, as long as the quantum state is guaranteed to have this tensor product decomposition. So that's a very kind of big requirement on the quantum computer. Indeed, most operations will introduce entanglement into a quantum state. But we haven't really gotten too much into the details of quantum entanglement, but we've really already defined it. Any quantum state that cannot be written down as a tensor product of its individual components is a quantum state that is entangled. Just like in the classical case, we said, hey, if you've got 2 classical probability vectors, you take the tensor product of them, you get a larger probability vector. But then there are larger probability vectors that cannot be decomposed. Those classical vectors were said to be correlated vectors. So you see how entanglement is really just a quantum version, in some sense, of classical correlation. We'll be seeing an example of this in just 2 slides. All right. Okay, so I'll kind of just quickly review the slide and leave it for you to kind of do the examples and exercises in the Jupyter notebooks. I mentioned last time, because of the simplification that we are doing of the quantum state to have its amplitudes just be real numbers, you can think of the quantum state as just a unit vector on a unit circle, and then all the operations that we'll do. So for example, you could do a rotation on this, right? So that means there are a class of operations that I could do on a quantum state that will amount to just your standard rotation vector, right? And you can visually kind of understand the geometric interpretation of that operation would be that, hey, whatever my state was, I'll be rotating that quantum state around by an angle theta. Some popular and commonly used operations, for example, would be the X operation, the poly X, which we've already seen is also a classical NOT operation. But then a slightly different operation is the Z operation, which is 1, 0, 0, minus 1. So X is also a valid classical operation, but Z is not a valid classical operation, but it is a valid quantum operation. And so you can verify Z applied to 0 will give you just the 0 state back, but Z applied to 1 will give us the minus 1 state back. And so this minus sign is interesting, as we've noted in previous examples. And then Hadamard, we've already seen, is 1 over square root 2, 1, 1, 1, minus 1. What I leave as an exercise for people to try to work out via the Jupyter notebooks is, what is a nice way to visualize or think about the geometric result of applying X, Z, and H on a quantum state in the unit circle. What's the net effect of this operation on the quantum state? All right. There are a bunch of notebooks already that talk about rotation and reflections. They will lead you through it. And so you can work on them in terms of understanding them as rotations or reflections on the unit circle. All right. So quick summary of what are the three kind of main rules that we have picked up from quantum mechanics for quantum computation. If you've got an n quantum bits, the system looks, the joint probability vector, the joint quantum state looks like this. We observe how this is not really a probability vector, but slightly different. And the constraint is that the sum of the square of the amplitudes equals 1. Through it, we get this notion as well that, hey, when I observe, I get index I as a measurement result with probability alpha sub I square. And if I evolve my quantum state, that undergoes essentially unitary evolution. That means I apply U to psi to get a state phi, and I'll have the constraint that, well, I'll just get a new state with amplitudes beta sub I rather than alpha sub I. So those are the three main kind of things that we are getting from quantum mechanics that we'll now implement in quantum computation. And we'll finally get started with two basic kind of quantum protocols for quantum computation. You'll see Grover's algorithm in our session on Friday. Claudia will make you work through some actual examples using notebooks, but let's actually see examples of two non-trivial protocols that really were some of the pioneering examples of, hey, quantum protocols can do, and quantum information can do things slightly differently than classical. Towards that, first, one key resource, as we've already referred to entanglement, is how do you prepare an entangled state, or indeed a maximally entangled state? So you essentially use the circuit. You start with 0, 0. You apply Hadamard to the first qubit. So that will give you Hadamard tensor identity, which will give you then the plus state in 0. But then now you're applying C0, which is a joint operation. So let's write this plus 0 slightly differently, right? Let's expand it out. This will be 1 over square root 2, 0, 0, plus 1, 0. Right? You note now at the moment, this state is not entangled, because I can really write it down as the plus state tensor product the 0 state, which is just this expanded form. Right? Now, however, when I apply C0 to this state, what do I get? Recall C0, basically the first qubit is control. Here the control is 0, so nothing happens to the second qubit. Here the control is 1, so the second qubit will get flipped. And so I'll get 1 over square root 2, 0, 0, plus 1, 1. And so this is, as I mentioned previously, the example of a 4-dimensional quantum state that cannot be written as a tensor product of just one quantum bit tensor another quantum bit. Even though indeed initially when we started out, it was really 0 tensor 0. But when we did this entire computation, Hadamard, in fact, is also still just a single qubit operation. But the C0 that we already reviewed last time is not just something on first qubit tensor, something on second qubit. It really creates this entanglement between these two qubits such that the resulting state now cannot be written as something on qubit 1 tensor, something on qubit 2. It's really its own thing, right? So it's something that you get from the combination of the superposition the Hadamard creates plus the interference created by C0 to get your entangled state. So this is an example of your Bell state, which is a class of maximally entangled states. All right. And why is this important? Well, because we'll just use it as a resource in two basic primitive protocols for quantum computing. One is called the Superdense coding protocol. So basic kind of review of the protocol itself. Whenever you see these two lines, parallel lines together, that means evolution of classical information. So A and B are classical bits. And so this is that classical information evolving over time. Here you've got just this one line over here and single thin line over here. These two together make up two quantum bits that we are saying are the entangled state 5 plus, which is the name we give to this Bell state that we have over here as well. So 5 plus is the notation that we attach with the entangled state 1 over square root 2 1001. So what's the understanding of the protocol over here? The idea, we've got two scientists, let's say Alice and Bob. They're spatially separated, but they did meet at some point, or they interacted with a joint third party who distributed among them the state 5 plus. So the idea is this state 1 over square root 2 0 0 plus 1 1. The first qubit from here is the one that Alice has, and the second qubit over here is the one that Bob has over here. So even though this is a 2-qubit system that is entangled, it is still possible for us for sure to take the first qubit and give it to Bob, and the second Alice, and the second qubit given to Bob. And now Alice and Bob go their way. Right? Bell state is a general name to a class of entangled states, right? There are other classes of entangled states as well. And now we have this protocol that will say, essentially allow us to communicate these two classical bits from Alice to Bob, assuming Alice went to Venus, Bob went to Mars, or vice versa. And then Alice wanted to communicate A and B to Bob. But Alice did not have a classical communication channel with Bob, let's say. So what Alice will do now is produce some kind of computation that links this A and B to her share of the quantum state that she has entangled with Bob, which is this state over here, right? And then this state is transmitted to Bob, right? So this dotted line is kind of signifying the spatial separation that exists between Alice and Bob, and Alice is then sending the state to Bob after doing two operations to her state, to her share of the state 5 plus. Now, what are those two operations? This one we've already seen before. This is just the C0 operation, the control naught. This one looks kind of similar, but it's got two filled in circles, but then there are -1 over here. This is just another way of drawing what we call the control Z operation. Just like this was control naught, or you could also call it control X, because the NOT gate is also the X operation. So similarly, you get the idea that this one then is just, this is the control bit, and wherever you see the -1 written, the idea is you're applying the Z gate on the target bit. The -1 is essentially referring to that phase that we had over here, right? That -1 entry that we had in the Z gate. And then there's some kind of processing that Bob will do once he receives Alice's state. And then the claim at the end is that Bob will receive exactly the values A and B in his share of the two states that he had. So the 5 plus that they had will essentially evolve to just the state AB. So in some sense, the entanglement in 5 plus will be consumed, and Alice and Bob will be left with AB. And so our summary would be that Alice has transmitted one quantum bit, and through that transmission has given Bob two classical bits of information via just one quantum bit. All right, let's see it all in action. So the way we'll do it is just fill in kind of this table where we'll slice the circuit that we saw in the previous example in a bunch of levels. So time 1 is the time naught is the initial state. T1 is after applying control Z. T2 is after applying C naught. T3 is after Alice has sent her quantum state, and then Bob applies his C naught, and then Bob applies his final Hadamard. So the first few applications of this protocol are relatively straightforward, right? What happens here now? We start in the state 5 plus, right? So the two quantum states are 5 plus. State at T1, note when A and B are both 0, 0, both the control operations will not get applied because both the control operations have the control bit set to 0. They're not switched on. So we'll keep the state 5 plus over here. We'll keep the state 5 plus over here. The state doesn't change because neither of these two operations will get applied because the control bits over here are determined by A and B, and we have fixed A and B both to be 0. Right? Now, state at time t3, at time step t3, Bob is applying C0 with the first bit as control and the second qubit as target. So 0, 0 obviously will not change. 1, 1 will become 1, 0. So the state on Bob's end will become 1 over square root 2. So now note, both the qubits are with Bob at time step t3. In fact, at this point as well. So you've got 1 over square root 2, 0, 0. But now rather than 1, 1, I've got 1, 0. And this can be rewritten as 1 over square root 2, 0, 0. Let me write that separately. 1 over square root rather than this. Observe that this can be written as the plus state tensor the 0 state. Right? Because this is 0, 0, this is 1, 0. The second qubit is always 0. You can kind of take it out. And so the first qubit is really just in the plus state. The second qubit is in the 0 state. Now, at time step t4, Bob just ended up applying Hadamard to the first qubit. Well, the first qubit is in the plus state. You apply Hadamard to it, it goes back to being the 0 state. So you get 0, 0 out. So that's exactly what we had over here. AB was 0, 0. Bob, indeed, in this case, is left with 0, 0 on his end as well. Right, so we're off to a good start. It's exactly doing the kind of computation we hoped would have happened. And this kind of is something that we then keep verifying. We start off with the second case where now AB is 0, 1. A is still 0. So this means this control operation will not get applied. So at time step t sub 1, we don't get a new state. We keep the original state's definition because the control Z operation didn't really get applied. So we just get 5 plus out again. However, at time step t sub 2, though, now we will get a slight modification because B is 1. Well, B is 1, so that means 5 plus will now get changed. But what part of 5 plus will change? The first qubit or the second qubit? So I'm trying to write down the state over here. Will the first qubit change or the second qubit? Note, Alice has the first qubit. The target operation, the target qubit is the first qubit. The control in this case is actually a classical bit. And so the target is the first qubit, which is with Alice. And so the first qubit undergoes a change. What will the state become? 1 over square root 2, 1, 0. Oops. 1, 0. And then the 1, 1 will become a 0, 1. Agreed? This is the combined state that Bob will have when he applies this C0 to get his state at time t3. Well, again, it's now in this case, the C0 is being applied with the first qubit as control and the second qubit as target. Let me just make this clear. So this was, oops. This was 1, 0. Right? So now, in order to get the state at time t3, the first qubit is control, the second qubit is target. 1, 0 will become 1, 1. 0, 1 will remain as is. So we get 1 over square root 2, 1, 1 plus 0, 1. And you now note the first qubit is still in the plus state, but now the second qubit is always in the 1 state. So this is equivalent to plus 1. Hadamard again gets applied on the plus state, you get a 0. And so as we might have hoped, you get 0, 1 over here as we would have liked. And so hopefully everyone gets kind of the gist of what's happening. It's really just plug and chug. You do the computations, and I leave it as an exercise for everyone to verify that indeed in the remaining 2 cases as well, you will indeed get exactly what we would want. In this case, you get 1, 0. In this case, you'll verify that we actually end up getting minus 1, 1 rather than 1, 1, just 1, 1. But the minus sign doesn't really matter because when we'll kind of take the amplitude square, the minus sign doesn't really make a difference, right? So I'll leave kind of filling in these entries over here as an exercise for you to figure out how these get filled in. And so that will allow you to convince yourself that this protocol known as superdense coding has allowed Alice to transmit 2 classical bits at the expense of transmitting 1 quantum bit and also having prior shade entanglement between them. So we assume that Alice and Bob already had 5 plus shade between them, right? Right, as Jaden notes, that this state over here, again, is a maximally entangled state, as indeed you will have in all the 4 cases over here. You will end up creating a basis of the 4 Bell states over here. All right. I'm sorry, I'm going slightly fast. We're really pressed for time. I'm already kind of eating into Claudia's time. Hopefully she'll allow me to have 10 more minutes to kind of make sure that I complete the key things that are required. Is that okay, Claudia? I think you're already there, right? Could I have 10 more minutes?
Yeah, please, Jibran.
Okay. All right, thank you. Where does the minus sign come from in the last row? Good question, but as I mentioned, I'm not doing the computation right now. You'll quickly just verify once you do the computation that the minus sign shows up, right? You have this plus state and the minus state. Remember, there's this Z operation happening over here, and Z applied to the 1 state gives you a -1. So there are those things that can potentially kind of allow you to get that minus sign. All right, but you can just do the computation and it will kind of follow through from there. All right, so this perhaps doesn't seem that interesting because, well, okay, 2 classical bits transmitted by 1 quantum bit, but who has a quantum bit sending channel these days, right? So great, but so what? So let's do something slightly more interesting, which almost is the inverse of the previous operation and is where, you know, quantum teleportation comes in as well. Perhaps it's a misnomer. I'll let you be the judge of it. IBM famously ran an ad in Scientific American as well that kind of in early 90s, suggesting that, you know, IBM is working on actually teleporting soup from one place to another. Unfortunately, we are nowhere near, after even 30 years, to teleport soup, even quantums. Well, I don't know about quantum soup, but definitely not the soup that we make in our kitchen so far. So this is not the Star Trek kind of teleportation, unfortunately. Whether or not it should qualify as teleportation, I'll let you be the judge of that. What does the protocol circuit look like, right? We've still got our friends Alice and Bob in the notation, and then they're spatially separated. They still share this 5 plus state. There's, you know, maybe Charlie sent it to them, or they met earlier and shared it among themselves. But now Alice is starting off with some state psi. And what's nice to observe or make a note of is that this psi can be completely unknown to Alice, i.e., David came along and gave Alice a black box in which there was this state psi. Alice has no information about what this state actually is, right? Alpha and beta are not known to Alice. Alice will perform some kind of operations, perform measurements after those operations to generate 2 classical bits, and then transmit those 2 classical bits to Bob. Bob will again perform some classical transformation, some quantum operations, and then our claim in the circuit is Bob will obtain exactly the state psi on his end as Alice had in the beginning. And so someone asked what this -1 is. This -1 operation is exactly the -1 that we had in the superdense coding as well. That is, this is a control Z operation. So you can think of this as essentially just the Z operation being applied, control on the value of this bit. Alrighty. So crucial kind of things to note. Even though Alice did not know anything about psi, Bob, we are claiming, is going to obtain exactly the state psi at the end of this protocol. Something that's not obvious in this visualization of the protocol, had the state psi been shared with, you know, some other party Charlie, some other state that some other party Charlie had, then this psi would also be shared with that state that Charlie had. So that's really cool, and a practical way in which quantum teleportation is actually used to spread entanglement across parties. You can kind of do this pairwise kind of teleportation to spread entanglement across. And then also note that in some sense, partially why you're getting the name teleportation associated with it as well, is that this is kind of a perfect transmission in some sense. As you know, it's relatively straightforward to send 2 classical bits without error. And then this alpha is going to be reproduced precisely on Bob's end. We aren't doing any kind of epsilon parameterization over here. The claim of this protocol is that exactly the value alpha that we had for state psi over here is what is reproduced over here. So alpha could have been some arbitrary long, expansion of a binary digit, which corresponds to all the works of Shakespeare in English. That exact alpha is what appears over here in this psi as well. Unfortunately, as we've seen, it's not possible for Bob then to extract that alpha with just a single measurement, but it's still interesting that that exact information is being produced over here, and which then leads to finally building to the teleportation with that, hey, well, if you take some real macroscopic object over here, rather than just this, one quantum state, 2-level quantum state, and do this entire protocol, what will Bob have over here? So if this was my cat, not that I'm suggesting I would do with my cat, nor that I have a cat at the moment, but I don't know whether you would want to do it with your cat. Well, maybe you want to do it with a table, or I don't know, your pen. If, I had a perfect quantum description of some macroscopic object over here, obviously amount of resources I will need to do this protocol will increase, the amount of entanglement Alice and Bob will need and whatnot. Assume you take care of those technical details. Then quantum information and quantum mechanics is saying you will have a perfect replica of that object over here. And the object over here would be completely destroyed. So yeah, we're not making a copy. Right? So someone referred to no cloning over here, right? So this protocol would not allow you to make a copy of psi over here. You note how in this protocol over here, we are doing a measurement. As soon as we have done this measurement over here, whatever superposition we had over here is completely gone. So if you're okay of, losing your pen to have your friend Bob obtain your pen, perhaps this teleportation protocol is saying, hey, yeah, you could do that. Not instantly, because remember, you will need to communicate at the speed of light to send this classical information from your end to Bob's end. But indeed, you could potentially send any amount of macroscopic physical objects by just communicating some information or complete characterization of it in some sense. Well, not complete, some characterization of it in terms of classical bits, plus lots and lots of shared entanglement between Alice and Bob. Right, so that in some sense is where perhaps the motivation to name it as teleportation comes from. And so to which if you follow through with the sequence of reasoning, you say, well, what if this indeed was Schrodinger's, or indeed my cat, or myself? Would I really appear over here and, disintegrate over here? Lovely question to think about when having, I don't know, whatever your favorite drink is. And the really fun question to ponder, if you really take this to extreme, is what is the reality of the existence of whatever that object was when you are over here? Right, so I'll let you think about all these parts once you review this video on YouTube. That's really fun stuff. Anyhow, let's do the actual math. Okay, so I start off writing down the combined quantum state. The combined quantum state is psi plus phi plus, right? Hey, Antonio, I didn't ask that, you asked. Is there a soul? If there is a soul, can it be transmitted? Is it characterized in the complete quantum description of the object? I don't know. All right, so we've got psi tensor phi plus. All right, so this will be perhaps our last exercise in working out this expansions. So this is what? This is alpha 0 plus beta 1. Tensor phi plus, which is our entangled state 1 over square root 2, 0, 0 plus 1, 1. Right? Now, I want to apply a C naught, so it makes sense for me to combine the first qubit with the other two qubits, right? So that it will become easy to apply the C0. So let's kind of combine the first and the EPR pair or the Bell state. So I get 1 over square root 2. And then I get this parameters out, alpha with 3 zeros now, and then alpha with 0, 1, 1, plus beta with 1, 0, 0, and then beta with 1, 1, 1, right? So this is just the initial state rewritten in a joint description. The next step is to apply the first operation, which is C0 between the first two qubits and identity on the third qubit, right? So you understand there are 3 qubits involved. I do a control knot between the first two qubits, nothing on the third qubit. So that's why there's an identity there. And the C0 is first qubit control, second qubit target. And you can literally just read off the change. Nothing will happen over here because the control qubit is 0. Both these two cases will have a flip of the middle qubit because the first qubit control is switched on. So I'll quickly kind of just write it out. You'll get alpha 0, 0, 0 plus alpha 0, 1, 1. But now the modified part, beta 1, 1, 0, and then beta 1, 0, 1. Right? So that's our updated quantum state of 3 qubits. Next, I apply my Hadamard on the first qubit. So now the operation being applied is Hadamard, tensor identity on second qubit and identity on the third qubit. Now kind of things expand out a bit. So what will happen? I will essentially get an expansion of this thing into kind of 2 different bits, right? So you'll get the first qubit 0 being kind of expanded into kind of 0 plus 1. So you see kind of these 4 entries in the summation will now become 8 entries, right? And so that's why, you know, until we get a nice concise representation for applying Hadamards, these computations will end up being tedious. All right, I missed the 1 over square root 2 here. Maybe I'll just write it like that. Okay, that 1 over square root 2 becomes now 1 over half because of the application of the Hadamard. Let's just write it way up front. And then I get alpha 0, 0, 0 plus alpha again, but now 1, 0, 0. And so, you know, this is the expansion of the highlighted case in the previous line. So this thing actually expanded out into this thing, right? Plus, we'll keep on. I'll just keep writing and hopefully not make a typo. I apply Hadamard again on 0, so that's still the same thing. Alpha 0, 1, 1 plus alpha 1, 1, 1, right? So this is the expansion of this whole thing. And then hopefully you get the picture. But now that Hadamard gets applied on 1, so we also get a minus sign working in there. So I'll get a plus beta 0, 1, 0 minus beta 1, 1, 0, right? And then finally, plus beta 0, 0, 1 and minus beta 1, 0, 1, right? So maybe, and then this bit is this bit. Okay. All right, so this is probably the most, there'll be one more tedious bit, but then we'll be done. And then the protocol is relatively straightforward to verify. Let's kind of write down the terms grouped together based on the values of the first 2 bits. Why do we want to do that? Because, well, whatever happens on Bob's end is now going to be dictated by the values of the measurement result on the first 2 qubits. So let's just group exactly this state. We will just rewrite it, but we'll rewrite it by grouping the first 2 qubits together. So this can be just rewritten as half. And then I've got 0, 0, right? And then in this case, what do we do? Well, 0, 0 was here. And where else was 0, 0? Here. Well, in this case, there's an alpha. And in this case, there is a beta. And the third qubit is 0. And the third qubit is 1. So that means this will be alpha 0, plus beta 1, right? So let's quickly see. This is exactly what we might have hoped would work, right? In the case where the measurement result on the first 2 qubits gives us a 0, none of these 2 control operations will get applied. And Bob already should then have the state psi because these operations are not getting applied. And that's exactly what we see over here. The third qubit is indeed exactly in the state psi when the first 2 qubits are in the state 0, 0 after measurement. Now, what if that was not the case and the state was actually 0, 1? Well, then in that case, you can verify that, well, where does 0, 1 occur? So you've got a alpha 1 with a 0, 1 in this case. But then where does the next 0, 1 occur? Well, there's a 0, 1 over here, but now with beta, you've got this factor of 0. So we don't get exactly the state psi, but we see kind of it's very closely related to psi. So in this case, now we're getting alpha 1 plus beta 0, right? Hopefully everyone is following along. And then kind of the same pattern kind of in the case when it's 1, 0, there's a different kind of error. What's that error? Well, I've got alpha 0 minus beta 1. And then the final case, I'll just write it down over here. In the case where I've got the state 1, 1 on the first 2 qubits, then it's alpha 1 minus beta 0. And so you've got this as your entire kind of state. Let me kind of just do a visual inspection. So I've got 0, 0, I've got psi, all done. If I get 0, 1, then the state that Bob has over here is alpha 1 plus beta 0. Well, what operation should I do on alpha 1 plus beta 0 to make it psi? Anyone in chat, if you're following along? X, all right, awesome. And indeed, we go back and see, well, that's exactly what the protocol is dictating for us. In the case when the second bit sent by Alice is 1, this control not gets switched on. And so the X operation does indeed get applied. So this 1 corresponds to this C naught actually getting activated. So a NOT gate will indeed get applied on the state. This bit has value 0 over here. So the control Z will not get applied. And so indeed, when you look at the final state over here, you will indeed get this state after application of the NOT gate is indeed psi again. Same idea over here. Now you've got 1, 0. So this is 1, this is 0. So the C naught does not get applied. The control Z operation now gets applied. Well, that's exactly the operation I need. Why? Because there was this minus sign in front of 1. By applying Z gate, this minus sign becomes a plus sign. I get exactly my psi state back. Awesome. And then, hey, this looks more complicated, but it's really just a combination of both an X gate and a Z gate allows me to recover the original state psi back. This really is a precursor to how error correction kind of also works. In fact, that's exactly kind of what's happening over here. So these are really kind of your syndromes that are identifying for you, hey, what error has occurred? And then the corresponding operations that get applied are the ones that are correcting for that error, such that in all 4 cases, we are guaranteed now to obtain the state psi on Bob's end. And hence, Bob has been able to receive the state psi on his end by just 2 classical bits from Alice and prior shared entanglement. So that's really cool, right? And so for sure, it's worthwhile to go back and look at the circuit for Superdense coding versus quantum teleportation, similarities and differences, what one is doing and what the other is doing. For sure, teleportation seems kind of cooler, but it's not instantaneous, right? So as I noted earlier, Bob would not know which operations to apply without receiving the classical measurement result from Alice. So in order for Bob to actually obtain exactly psi, Bob needs to apply certain transformations conditioned on the values he receives from Alice. So there is automatically that limitation of, well, the time it takes for information to be received from Alice's end. So this is not instantaneous teleportation. It is limited by the speed of light, right? Does Superdense coding scale exponentially? Unfortunately, no. One might hope that, hey, could I send more classical information in quantum states? We know that, in fact, the example that we've just done is optimal. I can't send more than 2 classical bits in 1 quantum bit. So it kind of, it's kind of intriguing and interesting that quantum stuff gives you more. So kind of going back and connecting it to our superpower, we get ability to do more interesting stuff with quantum, but then it's not like magic. There's kind of real nice, precise, calibrated kind of almost level of advantage that quantum information gives. And this in of itself is kind of one of the intriguing kind of projects in terms of figuring out what exactly are the limitations of what quantum computing and what quantum mechanics allows us to do, and why those limitations get implemented. Kind of going back to the rules of quantum mechanics and figuring out why those limits of quantum mechanics imply certain limits of being able to manipulate quantum information in a certain way, right? So there's a really nice kind of back and forth that can happen that, hey, if I were able to do this via quantum computer, the following kind of fundamental rule of reality would break. So it works kind of the other way around as well, right? So if a quantum computer could do this, then some rule of quantum mechanics would break, and vice versa. So there's a really nice way of, both these fields kind of benefiting, where CS benefits by new algorithms, and then us getting better insights in terms of physical rules and physical laws in terms of the consequences they have for quantum algorithms. Alrighty. So I realized today's session is kind of squished together more content, and there was more content that I would have liked to present as well, but I think I'll stop here. And it's totally possible that the remaining stuff is also covered by Claudia in her presentation, where she will work with you through Qiskit and some of the tutorials that we have in Jupyter Notebooks. You should work through those programming exercises. The purpose of the 2 sessions that we've had so far together was to introduce to you the basic fundamentals of quantum information in a more theoretical way. For sure, I expect that this to be not sufficient for someone who's just getting started. So it's strongly recommended to go back to the Jupyter Notebooks and review the programming exercises and tutorials there and work through them to make sure you actually do understand what I seem to might have been rambling on for the last 2 days, 2.5 days. All right, with that, I'll stop and take any questions before Claudia starts.
Can you also share, Jibran, what are the quizzes to be done for this lecture?
Sure. Pretty much all the quizzes, other than for the one for Grover's algorithm, which is the last one, are doable, except that I have not covered the notion of reversible computation. But other than reversible computation, everything else has been covered. So the first 4 quizzes are possible to do now. As I mentioned, though, that's kind of the ideal case where you already knew quantum computing. In order to really internalize this stuff, you should first work through the content in Jupyter Notebooks. For example, remember in the case of Superdense coding, I didn't work out all the entries in the table, work out those entries yourself manually, work through them maybe through the programming exercises. So you really actually get a feel of how those computations are working out. Similarly, when we did the visualization of quantum states under quantum operations on that unit circle, that's again programming exercise for you in the Jupyter Notebooks as well to see, all right, why does Hadamard correspond to such and such reflection? Why does the X operator correspond to such and such rotation or reflection? So those things are really some things you should work on more before attempting the exercises, the quizzes. Right.
Great. Yeah. Thanks a lot, Jibran, for that.
Thank you very much.
And following up the Discord questions, I think, Jibran, you covered most of the questions live itself. So that's amazing. If there are any more questions, I would suggest taking those questions from the live chat now to the dedicated QBronze channel, where you can continue the discussion. And I think, Jibran, you are also on Discord, so you can get everything.
Sure.
Welcome, Claudia. Claudia is a coordinator of the Q Education, the Q classes, the Q course, everything that's happening at QWorld. She is an amazing lecturer. She is also the research department leader at Quantum Pulpo. And she's also the teaching assistant at the Autonomous University of Mexico. And yeah, she's here to give us a demo on the QBronze worksheets and certain assignments and a demo as well. So over to you, Claudia. Please take it away.
Thank you so much. We are going to review some topics on the Qiskit and also the notebooks for QBronze, as mentioned. It is important to mention that the starting point for this tutorial is this notebook that is called Content. And in here you can access all the rest of the notebooks. And it is important that the notebooks are ordered by topic. So it's highly recommended that you always use it. You can choose to start with the review of Python and basic math, these two, but these are totally optional. But the rest of the notebooks are not optional, so please review them, since in there you can find a lot of details about the topics. So let's take a look at some examples of these notebooks. So here we have the two coin bias game, where bias means that the coins land with different probabilities on each of their sides. So here we are using probabilistic bits in the form of a coin as an example, in such a way that we can map each possibility of a bit with one side of a coin. Then for the game, we start by flipping one coin, and depending on which side it is shown, we will flip another coin. If it is heads, we will then flip another coin, for example, an euro. And if it lands on tails, we will flip a different coin. So in order to differentiate, let's say it is a cent. So in here we have the transition matrix. This is the summary of the game. We can see the probability with which we can get heads or tails. So in the top, we have the initial state. And on the left, we have the final state. Here, let's notice a couple of things. First of all, the name of the states, it's totally arbitrary. In our example, we are using coins, so that's why we are saying one possibility is head and the other possibility is tail. But we can easily choose a different symbol. So we can say, okay, I want to name the first state with a 0, and I want to name the second state with a number 1. But these are just symbols. It is actually not really important, as long as we can distinguish between the two possibilities. Second, let's notice that the values of each column add up to 1, since they are probabilistic states. So this number 1 indicates the 100% probability. The columns must always add up to 1. This is an important thing. And third, as noted here, the probabilities for the euro coin are in the first column, and the probabilities for the cent or the second coin are in the second column. So let's play the game. Like here, we are going to toss 3 coins or 3 times the coin. We are going to start assuming that we are going to flip the first coin of the euro. That is why it is indicated that the side, it is heads. I mean, this indicates us that we are going to start with a euro. And after that, we are going to make the actual first toss. And with that, we are going to calculate the new probabilities by using the information of our matrix. Let's remember the matrix. We had, if we start in heads and land in heads, we have the probability of 0.6. And if we start in heads and end in tail, is the rest of the probability. And for the second coin, we have these probabilities, right? So this arrangement is also known as an operator, as well as a transition matrix, as I said. Thus, the probability of heads in the previous, the probability of getting heads is going to be calculated by, okay, I start in heads, and what happens if I end in heads? I mean, I toss the first coin and get heads, so I am going to have that in 60% of the times. That's why I am taking the 0.6 and multiply it by the original probability. So if I start in heads and end in tails, I am going to take that probability, okay? But if I start in tails, but still end in heads, so I am going to take that for the probability of getting heads for after the first toss, all right? So I do the same process for all the tosses. Basically is recalculating the probability with the same logic. And after that, I recalculate the probability. At the end, we have we can see that each toss modified the probability of getting heads at the end after 3 tosses, and as well as getting tails after 3 tosses, okay? And we can see that these two numbers add up to 1 because this is a probabilistic states. So it is really easy to take this and define some code to decide many more tosses just by using a loop. For example, in the task 2, we are asked to toss the coin 10 times, but we don't want to repeat this code 10 times. So that's why we create a for loop. And after all the tosses, we calculate the probability in the same way because we are using the same transition matrices each time, right? So after that, we see that after 10 tosses, the number changed a little bit, not so much. So we can see that the probabilities are getting to get some fixed number. So for example, for the next task, you need to do the same thing for more iterations, and you can conclude that this game is going to converge to some value, to some fixed value. So this is for probabilistic state. But let's check now having 2 probabilistic bits. For example, let's take these 2 over here. And let's remember that each vector represents a probabilistic state for each bit. And we now want to see the 2 states as a single state. Let's see, let's think we have 2 coins and we want to toss them at the same time. So what I can get at the end? I can get the first coin has heads and the second also has heads, but we can also have the combination of head tails or tails heads. or tails, tails. And if you remember, we can rename this with 0, 0, 0, 1, 1, 0, and 1, 1. I am just changing the symbols that represent the possible outcomes. So with this, we can see that for 2 coins, we can have 4 possible combinations, right? And we usually represent these combinations with zeros and ones. That's why I am mentioning this. So now let's see the representation. To write the basis vectors, let's facilitate this. We are going to define the vector 1, 0, and I am going to assign this symbol. And also I am going to define the vector 0, 1 and assign this symbol. So I am only finding a way of writing vectors in a more compact manner. So for example, let's say this example, we can also be written like 0.2 multiplied by the vector 1, 0, right? Is the same. And 0, 1. All right, but we already defined a symbol for this. So we can write okay, we are just finding a way to write the same information in a different way. And we call these vectors as basis vectors. Okay, given this notation, we are going to define a way to express the whole system that contains two coins in this example. For that, we are going to use the tensor product. The tensor product is a mathematical operation that is represented by this symbol. And with this, we can find all the possible combinations. All right, so if we take the example from the beginning, take the tensor product, meaning we are going to find the whole system composed by the 2 qubits. And for this calculation, we need to arrange the elements like this. So at the end, we are going to have the probabilities of having each of the possible combinations. So 2 by 6 is 12, 2 by 4 is 8, 8 by 6 is 48, right? And 32. So these are the probabilities of getting, in this case, heads and heads. And this is the probability of getting heads and tails. And this is the probability of having this combination. And the last one is the probability of getting 2 tails. This is because we are working with biased coins. So, well, as a note, in the same way, we can combine the states of the basis vectors. So, for example, we can combine the basis vectors 0 and 0 and take the tensor product. And this is going to be equals to this, right? So we can see all the resulting vectors over here. You can check the detail, but it is really easy to calculate the tensor product of these simple vectors. So this is an important notation. It's working for the classical probabilistic states, and is going to work also for the quantum states as well. But okay, now let's move to quantum systems. And for that, we are going to use the SDK called Qiskit. This framework must be installed, and it is important that the version that we use is equals to 1 or greater than that. For example, here I have the version 1.1. And in order to install it, we are going to use this couple of lines. Basically, it's pip install, and if you are running it under the notebook, you need this symbol, the exclamation symbol at the beginning. And if everything goes as expected, you can run the following cells. If you don't got any errors, so Qiskit is installed and working as expected. These cells are only examples. You don't need to understand what is going on at this point. The only thing we care about is that we are getting something as a result and nothing, no errors. If you have any kind of trouble by installing, please let us know in the Discord server. In there, it would be easier to review any technical details regarding your particular case on your computer and so on. So we have Qiskit working. Let's talk about quantum states. Quantum states are also represented as vectors and have a very important characteristic, which is that the sum of the square of their elements must be equals to 1. That the length of the vector is equal to 1. So for example, these vectors over here are not quantum states because the sum of the squares of is different from 0. For example, let's take the first one. We take the square of the first element is 1/4 plus the square of the second element is 1/4, and the sum of that is a number less than 1, so it's not a quantum state. Same thing happened for the second example over here. The sum of the square of the elements is greater than 1, so it is not a quantum state. It is a vector, but doesn't represent a quantum state. And at this moment, I want to mention that when we have a quantum state, the elements of the vector are called amplitudes. Well, common notation for the quantum states is like this. So this is ket. This is called bracket notation, also called Dirac notation. And it's a way of writing a quantum state very compact. I mean, this expression represents all of this. It is really more easy to write it like this. And in order to validate the length, we can use this expression. This is meaning that we are going to take the inner product of the vector with itself, basically. So when we calculate that inner product and we get that it is equals to 1, we can say that this is a valid quantum state. So for example, these vectors over here have an incognita like this. For example, this ket u. Here, this is a variable called b. So the task is to find which value of b is going to give us a valid quantum state. So for that, we take each element, remember, take each element, take the square, sum all the elements, all the square of the elements, this is B. And we want to be, to this vector to be a quantum state, so this is going to be equals to 1. We clear the variable B. This is equals to 1/6. So it is clear that B is equals to 6, right? So by doing this, we can say that when B is equals to 6, then this vector is going to be a quantum state. Please note that this vector has 3 elements. So now for the other example, the ket B, we have 5 elements and we have one variable called A, and the task is to find such value that ket B represents a valid quantum state. Of course, we can do this by hand, by making the calculations, but also we can do this by writing a piece of code. So we know that we are going to take the values that we already know, these ones, and we are going to take the square of that, then sum them up, all of them, and we are going to take 1 minus that value, and after that we are going to take the square root, and in that way we can find the value for the variable A. In this particular example, we have that A is equals to 0.7, but it can also be equals to the negative of that, because if we take the square, we can see that this expression is valid. So A can be equals to 0.7 and also can be equals to minus 0.7. Both values is going to give us a valid quantum state. Now the quantum operator is going to be represented by a square matrix that preserves the length of the quantum state. This is a very important thing because when we apply an operator to a quantum state, we want to still have a quantum state after that. So that's why the operator has to preserve the length. So in general, we are going to write this. We are going to have the operator represented by a matrix. And we are going to multiply the matrix vector multiplication. This is the operator. This is a quantum state. And the result of this must be a quantum state. So this is a vector. The result is a vector, right? And the size must be logic. I mean, if we have a matrix of size n by n, remember that must be a square matrix. So the vector must have a size n by 1. So these two are the same value. And the resulting matrix is going to be n by 1, right? So everything works very well because we start with this state and we are going to finish with a state of the same size. In order to write all the, we don't want to write all the elements of a matrix, neither all the elements of the elements of the vector. So we can also use the Dirac notation. For that, the operators usually have a letter that represent them. In this case, for example, the Hadamard operator is represented by the letter H. So if I write H, I am referring to the whole matrix. And I am going to multiply on the left to a quantum state, let's say the ket U, and this is going to give us, as a result, another quantum state, let's say the ket W. So for the next task in this notebook, we are asked to generate a random quantum state. And we know how to do that because we know the rule that the vector has to have a length equals to 1, right? And the task indicates that after generating that random state, we need to apply the Hadamard gate and validate that the resulting vector is still a quantum state. So in quantum computing, we usually limit the quantum states to vectors of 2 elements. The previous examples, we had examples with 3 elements and 5 elements. Okay, those are valid quantum states, but in quantum computing, we are going to use vectors with only 2 elements. That is, we will use 2-level systems states. And we call that kind of quantum states like qubits. So this is going to be limited to only 2 elements. And this is what we call qubit. That's why this function defines only 2 entries, first entry and second entry, because we want to work with qubits already. And here I am going to make a parenthesis to tell you that there are 2 qubits, two special qubits that we know as basis states, similar to the classical case. But now we are going to write these symbols using kets. So the ket 0 is going to be the state represented by the vector 1, 0, and the ket 1 is going to be represented by this other vector. We can quickly see that they have a length equal to 1, right? So they are quantum states, of course, and they also has only 2 dimensions. So these are qubits. So continuing with the function, we define 2 entries. We define 2 random numbers in this range. And after that, we calculate the length, because we want to normalize the entries. I mean, we can define any random number, but in order to have a quantum state, we need that the length is equal to 0. That's why we need to make this normalization process. So in this part of the code, the only thing we are doing is to avoid the case in which both entries were equals to 0. It has low probability, but it could happen because in this range, the 0 is included. So after we validate that, we perform the normalization, meaning that we take every value and divide it by the square root of the length. And finally, we return the vector with the 2 entries that we know those entries are normalized, so that vector represents a quantum state. After that, we are going to make a function that validates the quantum state. Basically, we are going to take each element, sum the squares, and check that the value of the resulting sum is going to be equals to 1. And in order to avoid the inaccuracy for the computer, we are going to define a threshold. So if the number is really close to 1, we are going to consider it as a valid quantum state. After that, in the function Hadamard, the thing that we are doing is performing the matrix vector multiplication. We receive as a parameter the quantum state in the form of a vector. So here we are doing that multiplication and returning the new vector. And while part of the description of the task is to perform this 10 times. So for each iteration, we are going to define a random quantum state, check, validate that is indeed a quantum state. We already know it is because we make a good implementation in this function, but anyway, let's validate it is a quantum state. After that, we apply the Hadamard gate, meaning that we multiply the matrix by the left. And after that, we are going to validate that the resulting quantum state is still a quantum state. We can see that for any random state that we generate, after applying the Hadamard gate, we are having a quantum state as a result. Okay, so this is the main idea of the task, that you apply the knowledge that you are reading in the notebooks. So now let's move to this other topic. Now, what about 2 qubits? In a similar way to what we saw in the classic case, we will be able to combine the quantum states to create larger systems using the tensor product. So we are going to write this using kets, for example, ket A, tensor product KB. So with this, we are combining 2 qubits to generate a bigger quantum system. This is going to be written, this can be also written like this. It's the same thing, and also this is also the same thing. This notation is the most common, by only writing the elements, okay? So all the possible combinations that we can have, considering the basis states, are going to be 0, 0, 0, 1, 1, 0, and 1, 1. But this time in form of kets, because we are talking about qubits. Well, this is short for all of this, right? And also, well, we know that the ket 0 is this vector, and we take the tensor product. We are going to have this vector that has 4 elements. So because has 4 elements, we are representing a system of 2 qubits. All right, in this case, we have 2 to the 2, this is the number of qubits, equals to 4. Okay, for the case of 3, here are all the possible vectors, right? But for the case of 3 qubits, we are going to have 2 to the 3, this is equals to 8. 8 possible combinations. The possible combinations are okay, and for example, if we check the first one, the state 0, 0, 0 is the same as taking the tensor product of 3 qubits in the state 0. And if you perform all the 3 tensor product, you're going to find that this is equal to this vector. This vector that has 8 elements. And okay, you can find by applying the tensor product, the whole vector that represents the quantum system, okay? But we can do this in a very easy way. For that, we are going to notice that this value, this 000 represents a 0 in decimal. This represents 1 in decimal. This is 2 in decimal, 3, 4, 5, 6, and 7 in decimal. So we are going to use this value as the index in which we are going to write the 1. So for example, this, in the index 0, we are going to start counting in 0 is where we are going to write the number 1. So that's why the number 1 was written here. But if, for example, we want to write the complete vector for the state 001, we are going to start counting in 0, 0, 1, 2, 3, 4, 5, 6, 7. And this is the state, the vector that represents that state. And if, for example, we take the state 1, 1, 1, we are going to write the number 1 in the 7th index or the 8th position. 0, 1, 2, 3, 4, 5, 6, 7. And this is the corresponding vector. And this same logic can be used for any quantity of qubits. So that is the task 2, what is asking in general, how can we define the vector that represents a system with k qubits? Well, the answer is we take the value as a binary representation. We find the decimal representation, and this is going to tell us the position of the number 1. Okay, so now let's check. I want to apply the Hadamard that we already saw to 2 qubits. So for that, we are going to define a quantum circuit. In Qiskit, we only need to define an object of this type. The parameter is the quantity of qubits. And the Hadamard gate is going to be applied by calling the method H. And this parameter corresponds to the index of the qubit. As simple as that. It's really easy to create quantum circuits and gates. And this line is to draw the circuit. Okay, so let's check some stuff here. Let's note that every qubit starts in the 0 state. All of them. A quantum circuit is read from left to right. So the first thing that we find in that order is the first thing that is going to be applied to the qubit or qubits. Each line represents a qubit. And the quantum gates are the things that interrupt that lines. So for example, this small quantum circuit can be written in a mathematical form like H, tensor product H, multiplied by the quantum system represented by these two qubits. So in this notation, we are going to apply in the same order the gates. So this H is going to affect the Q0, and this other H is going to affect the Q1. This, of course, is also the state 0, 0 because they start in 0, 0. And here we can see that we can write the tensor product of two Hadamard in this way. So we can also see this as a single 2-qubit gate. This is going to be just one gate. This is also Q1 and Q0. This is just notation. Maybe you can find something like this, but internally, this bigger gate is going to have this decomposition. So it's just a way to draw the circuit. So here, let me tell you that this is the amount of Hadamard gates we want to apply. And this can be any number. Of course, we need to have the same amount of qubits. Here can be 32, for example. So I don't want to write 32H. So that's why I use this notation. And the equivalent math matrix for this is going to be obtained using, again, the tensor product. So we take the H matrix, tensor product, another H matrix. And if you perform this operation, you are going to have this bigger matrix. In this case, is 4 by 4 because it's an operator that is going to act over 2 qubits. And of course, we can do this by hand, but also we can ask Qiskit to give us the information of the resulting matrix. For that, we are going to use the unitary simulator that is part of Qiskit Air. So we execute the simulator on the quantum circuit that we defined above. And then we obtain the result and we can ask for the unitary. So the operators, the quantum operators are also called unitary or unitary matrix because of the reason that they are length preserving. That's why it is called unitary. It preserves the length of 1. So we get this get unitary give us a NumPy matrix, but we can iterate over each element, so we can see that we are obtaining the same, right? So here is written in fraction, and here is written in decimals, but are the same values. We have all the flexibility. I mean, in this example, this is equivalent of writing H tensor product I. This is the identity operator, meaning that we are not affecting the qubit in any sense. And we are going to apply it to the quantum state of 2 qubits, Q0 and Q1. And again, this is going to be applied to Q0, and this is going to be applied to Q1. And in order to get the corresponding unitary or matrix that represents the operator, we can use Qiskit in the same way. And we can see that the resulting matrix is this. Here I want to mention that 1 over the square root of 2 is equals to, well, almost equals to 0.707. That's why we have a lot of these elements. Actually, this represents 1 over the square root of 2. And in the following parts of the notebook, you can check what is the effect of applying 2 Hadamards to the different combinations of the states of 2 qubits. For example, apply Hadamard to 0, 1, or apply Hadamard to 1, 0, apply Hadamard to 1, 1. You can check the detail here. So now let's talk about a little bit about the CNOT operator. So this operator is going to take 2 qubits. One of them is going to be the control. That is why we have this C is for control. And the other qubit is going to be the target. So if the control is equals to 1, the target is going to be flipped. Or we are going to apply the X gate. So let's remember, if the X gate applied to the gate 0, the result is the gate 1, and X gate applied to the gate 1 is equals to the gate 0. So the CNOT, for example, in here, we are going to take the control, the qubit on the left. So when the control is equals to 0, we are doing nothing, right? So the final state is going to be the same. But if the control is equals to 1, we are going to apply an X gate to the target. So this was 0, and after the CNOT, this is going to be 1. And this is 1, and after the CNOT, this is going to be 0. And this is the matrix representation of the CNOT. So if we apply CNOT to the 1, 0 state, which is this, and perform the matrix vector multiplication, we are going to obtain a new vector that is going to be the resulting of that, right? So this is the 1, 0, and this is the CNOT. This is 1, 1. Right? We can confirm that everything is working. And this is just an example. We can, of course, take the control, the other qubit. For that, we usually note that as sub-indexes. If we want the control to be the other one, we are going to specify it like this, or like this to be very explicit. And with this, we are indicating which one is the control. And in Qiskit, this is going to be really easy. We are going to use the CX method. CX is the other name for the CNOT because it's control X, meaning that we need a control in order to decide if we apply the X gate. And the symbol for the CNOT or CX gate is this one. And we are going to have a dot over the line of the qubit that is the control. And we are going to have a circle with a plus sign inside over the qubit that it is the target. And in this example, we have these gray boxes that indicate measurement. So we are telling the circuit that we want to collapse the state of the qubit 1 and qubit 0 and store the result of that collapse in a classical register. Okay, for that we are going to create the quantum circuit specifying both things. The first two indicates the quantity of qubits, and the second number indicates the quantity of classical registers or bits. So we use now the air simulator. We execute it over the circuit. And after that, we are going to measure the 2 qubits. So in this case, we are applying at this point, we have the 0, 0 state because the qubit starts on 0. And after the C naught, we also have the 0, 0 state because the control is equals to 0. So at the end, we are going to measure 0, 0. All right, but what happens if we change one of the qubits? For example, this one. At this point, we are going to have the 0, 0 state, right? But then we apply an X gate to Q1. So here we have the 1, 0 state. Now, after applying the C naught, we have the 1, 1 state, right? Because the control was 1. So at the end, we are going to measure both qubits, we store it on the classical register, and this is what we are printing. And indeed, we have the resulting state as 1, 1, as expected. You can check all the 4 cases. And the next tasks are similar. So now let's check more complete example of a quantum circuit. The quantum teleportation quantum circuit that you already checked a few minutes ago. And for this, let's remember quickly that we need 3 qubits. The qubit over here is going to store the state that we want to teleport. This qubit is the Alice qubit, or in this example, Asya qubit. And the third one is the Bob qubit, of Alvis in this example. So let's go directly to the final circuit. Okay, as mentioned above, this is the qubit that is going to store initially the state that we want to teleport. This qubit belongs to Alice. This is the qubit that belongs to Alice and is going to be entangled with the Bob qubit, and this is the Bob qubit. And we are going to have a couple of classical registers to store the mid measurements. So the first thing, well, the very first thing is to define the state we want to teleport. For some reason, we want to teleport that state. In this particular example, this state is generated randomly. So the next thing to do is to entangle the Alice, one of the Alice qubits and the Bob qubit. For that, we perform these gates. These gates are going to generate a Bell state. And after that, at this point, the 2 qubits are entangled and are in the state. This is one of the Bell states, and this state is here. After that, we need a way to communicate the qubit that contains the state we want to teleport to the other qubits, right? So we are going to correlate them using these gates. Since the qubit that contains the state we want to teleport belongs to Alice, we only have access to the other Alice qubit. That's why we are correlating these 2 qubits, that the ones that are in the Alice possession. So after that, Alice makes a measurement, and depending on that, Bob is going to perform X or and Z gates. Right? So in terms of the code, we can define a quantum register with 3 qubits, 2 for Alice and 1 for Bob. And we define 2 classical registers just in order to have more order. And when we create a quantum circuit, instead of indicating the number of qubits and the number of classical bits, we can indicate the registers. And here we can indicate as many as we want, as long as the first ones are the quantum registers and the second ones are the classic registers. Then we decide the state to teleport as a random value. We need the information as an angle because we want to encode the information in a rotation, in this case, a rotation over the y-axis. So when we have the value of theta in radians, we are going to send it as parameter to the rotation over the y-axis gate that we can access with this method. And we are going to apply that rotation to the third qubit. Remember, we start counting, or we start the indexes in 0. That's why the third one has index 2. And why we are multiplicating by 2 here? Well, this explanation is in the notebooks. I invite you to check that. And if you will still have questions, of course, you can ask on the Discord server. Then we create entanglement. In this case, we know that this is a Bell state by applying the H gate and CX. Then we create a correlation between the Alice qubits. This element, this barrier, is only to visually have a separation. Barrier is this, but has no effect on the quantum state. So it's the same of having it or not having it, but it is nice to include it so we can see this separation, and it is sometimes helps to understand the steps and the quantum gates, the order of the quantum gates. After that, we apply the measurement over the Alice qubits, and we store each one on each quantum register. As we can see here, this is stored in C2 and this is stored in C1. It's very clear that it's are stored in different classical registers. A barrier, that means nothing, but help us visually. And then we have the post-processing that it is done by Bob. So we are applying an X gate with the condition that if we read in the classical register number 1, if we read a number 1, the resulting state as 1, if that is the case, then we are going to apply an X gate. And if we read a number 1 in the second classical register, we are going to apply a Z gate. This is part of the protocol. And after that, the next thing is to display the full circuit. And we want to read the final state. Okay? So we are actually interested only in the state of the Bob's qubit, right? But in the way that it is written here is going to give us the state of all the 3 qubits. So let's check. At the beginning, when we calculated the angle to which to rotate, we found the values of the initial state. So the initial state is given by AB. And the value of A is this one that depends directly on the angle. And the value of B is this one, okay? So let's check if we can read the same state at this point. So as I mentioned before, we are reading the state on the 3 qubits, these 3 qubits. But what happened? No, doesn't happen anything bad. The resulting values of the final state are this. This is the vector. So we know the first element corresponds to the combination 0, 0, 0. The second one corresponds to 0, 0, 1. These to 0, 1, 0. These two 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0, and 3, 1, right? And everything has 0 but these two. So we are going to take a look in the states 0, 1, 0, and 0, 1, 1. We can see that at this point, they are equal, okay? And this correspond in the order. So we have Q2, Q1, and Q0. So the qubit that belongs to Bob is this, as seen here, right? And we can see that we have values when these two states are changing. So we are reading actually 0 and 1 for the Bob qubit with a specific amplitudes that are these two, and these amplitudes correspond to the initial state. The initial state that we mentioned, it was represented by the vector AB. So A is equals to 0.9 and B is equal to 0.18. So indeed, we can confirm that at the end of the quantum circuit, we have teleported the quantum state to the Bob qubit. I hope this makes sense. This is everything for me today. Of course, if you have questions, you can ask them now or in the Discord server. The mentors, including myself, we are going to answer your questions. And of course, I ask you to review the notebooks and mainly the task, since these exercises are going to help you to understand better the concepts and also are going to help you to answer the quizzes on Canvas. Thank you very much for your attention.
Wonderful. Yeah, thanks a lot, Claudia. I think most of the questions that were there on Discord have already been answered. And otherwise, like you rightly suggested, you are there on Discord too. So if there are any technical queries, you can directly respond to them. To all the participants, I would suggest keeping the discussion live on Discord and take the discussion from the live chat to the QBronze channel where we can more closely monitor the discussion. Okay, I guess with that, we can end today's sessions. I'll just stick around for a couple of minutes more. If there are any particular questions, happy to answer them. But otherwise, thanks a lot, everyone. We won't be having a session tomorrow. The next session will be on Friday. And there's a keynote session by Dr. Will Oliver from MIT. So stay tuned and do not miss to attend that session.